Hey guys, how's it going? So we're gonna be looking at more of the Taylor and Maclaurin series. I'm gonna give a brief introduction of what they are, and I'm gonna use some applications of them with three functions. So what is the Taylor series or Maclaurin series? I'm gonna define the Taylor series first. So this is what my definition is. The Taylor series of a function is the polynomial approximation of a point x equal of a function at the point x is equal to a. And the Maclaurin series is basically just the Taylor series application, but at x equals 0. And there's a general formula that we can use. So for the Taylor, it's written like this. N is equal to 0 to infinity, the series, okay, from 0 to infinity, f, the nth derivative of a over n multiplied by x minus a to the power of n. The Maclaurin series, quite obviously, Maclaurin, is written like this. Very similar, but n equals 0 to infinity. Fn, since a is 0 here, Fn of 0 over n xn. And here I'll just, it's kind of obvious. I'll just say provided a is a real number. Now, there are a few assumptions we are making when we do this. So I'll just write them here. We are assuming that with these Taylor and Maclaurin series, we are assuming that f of x is continuous and differentiable on x equals a. That's pretty obvious. So with all this said, let's look at the applications first with the Maclaurin series, and then we can gradually expand our concepts out a bit. Yeah. So let's erase all this. I think there's this clear all my drawings thing. Okay, so let's start. E to the x Maclaurin. So remember that formula I talked about earlier for the Maclaurin series. I'm going to write it down here, and we can use it later on. Remember f n of 0 over okay, so we're just gonna apply this series directly in. So first of all, f of x is e to the power of x. F of x is e to the power of x, but as you know, the derivative will always be e to the power of x. So, which is equal to f prime prime x, which is equal to f, the nth derivative of x, which is just e to the power of x. Now, e to the power of x. Okay, so fn of 0 then, the nth derivative of x, at the point x is equal to 0 is just e to the power of 0, which is 1. So the Maclaurin series f of x can simply be expressed like this. From 0 to infinity, remember fn of 0 is 1, so we don't include it. So it's xn, just xn over n factorial. And we are done. Now, before I talk about sine and cos, I wanted to expand this further with a few extra applications. So let's say g of, let's call this function g of x. Let's say it were to equal to x squared e to the power of x. How about this instead? E to the power of x cubed. E to the power of x cubed. How do we express this? Okay, well, first of all, notice in the summation part, it only focuses on n, the variable n. It doesn't consider the variable x. So we can just strictly say this is x squared times the series of n equals 0 to infinity. I'm going to point out that this is e to the power of x cubed here. Okay, so I pointed out that this is e to the power of x cubed. You already know that like e to the power of x gives you this. You can substitute x with x cubed. So you get x to the 3n over n. And the Maclaurin for g of x is equal to, just plug it in here like this. Let's see, n equals 0 to infinity. X to the power of 3n plus 2 over n factorial. Now, basically, like I said, x squared did not have a direct influence on n, so we could have left it out and treated it like a constant. Yeah. It's usually good. Like we could have directly found the derivatives of g of x, but it would have been much more complicated. We knew what e to the power of x was for the Maclaurin series. So then we just did a bit of substitution and multiplied it, and we got the answer much quicker. So Yeah, let's move on. Let's move on. So Maclaurin cosec. Find the Maclaurin series for cosine of x. Now, as you already know, the Maclaurin series for any formula can be written like this. N is equal to 0 to infinity. Fn zero so f of x is equal to this all the time, any f of x. And we're just going to directly apply this formula with this series. But first, I'm going to find a couple of derivatives for cos x. So f of x is cos x. F prime is negative sine x. F double prime x is equal to negative cos x f triple prime is equal to, let's see, that's negative cos x. It's back to sine x, because the derivative of negative cos x is sine x. And f4 of x is cos x. And it's going to be the same thing. Like, so then the fifth derivative would be negative sine x. The sixth derivative would be negative cos x, so on and so forth. So I'm going to put dot, 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 because I'm not going to do this 1,000 times. So, yeah, and then you can just plug in f of 0 for this. So f of x, applying this formula, so f of x is equal to, so I'm going to write it again, the Maclaurin series, and we're just going to expand it out. Starting at n equals 0, and seeing if we can develop a pattern from there. Over xn. Sorry, no, I made a slight mistake. Yeah, sorry, n factorial xn. And this is thus equal to from n, sorry, I'm getting a little ahead of myself. So we're going to expand this out. So starting at n equals 0, f of 0 is 0, so that's 1, x to the power of 0 over 0 factorial. This is what you get when n is equal to 0. Minus, because here it's minus, fn, yeah, so 0 times, because remember, sine of 0 is 0, x1 over 1. This is just equal to 0, so we're just going to ignore it. Minus, okay, so now it's cos x, so we're on n equals 2 right now. Second derivative, that gives you, so negative 1, and then x squared over 2 factorial. Remember, we're applying this formula right now. plus the third derivative, so f prime of f triple prime of 0, that's 0 because sine of 0 is 0, x cubed over 3 factorial plus f4 of 0 cos x, cos 0 is 1, x4 over 4 factorial. And I'm gonna simplify this out a bit. So that's equal to this. This is equal to 1. That's minus x squared over 2 factorial. Plus, this is equal to 0. So we jump to this x4 over 4 factorial. And we start to see a pattern. Dot, dot, dot. I already did the 6th derivative. It's going to be x. So you would, if you wanted to continue one more, you could say minus x6 over 6 factorial if you wanted to, but like I already knew it. So yeah, spared you the hassle, to say the least. So back to this, we can express this in a series representation. I'm going to write out the series first and then show it to you. So n equals 0. Try to put it in a series representation when you can. Occasionally you get bits called the remainder, which is outside of the series. But if you can, put as many values into the series as possible. Here we can put all the values into the series. So there's no remainder. So here it's x to the 2n times -1 to the n over 2n factorial. And you can see for yourself that when you expand this out, it will equal these. I'll just put it out here. So at n equals 0, this is x to the power of 0. -1 to the power of 0 is 0. X to the power of 0. -1 to the power of 0. 2 times 0 factorial minus, or you can do plus. Okay, so x, now n is 1, so x squared, -1 to the power of 1 over 2 factorial. That's equal to -x squared over 2 factorial plus x4. Now n is 2, so 2 times 2 is 4, x to the power of 4. -1 to the power of 2 is just 1. And over 2 times 2 factorial, which is 4 factorial. Consistent with this, yeah, this is the correct representation. Let's move on to Synax now. Actually, you know what? I have a better idea. I'm going to erase everything except the top. Oh yeah, and we're changing it to Synax. All right, so here, Maclaurin series for Synax. Let's see. F of x is equal to this. Yeah, so let's find the first few derivatives of sine x before we proceed with this formula. So f of x is sine x. F prime of x is cos x. F double prime of x equal to negative sine x F triple prime is equal to negative cos x. And the fourth derivative is just back to sine x. All right, and I'll do one more just for this question. F5 is cos x. Okay, now we're gonna apply this Maclaurin formula down here. So f of x is equal to n equals 0 to infinity. So fn, yeah, let's just fn. What happens at n equals 0? At n equals 0, you get nothing because sine of 0 is 0. So let's skip at n equals 0. Let's go to n equals 1. At n equals 1, you get, so f prime of 0, that's 1 times x to the power of 1 over 1. I know this looks really funny, but I'm going to simplify this later. So don't worry about this for now. F double prime of x doesn't give you any value because negative sine of 0 is 0. So let's skip this. The second derivative, let's move on to what happens when n is equal to 3. When n is equal to 3, the third derivative will have a value of negative 1. So minus 1 x cubed over 3 factorial. F4 of x sine x. Okay, so the fourth derivative yields a value of 0 when you apply n is equal to 4. So let's move on to the fifth derivative. Plus 1 times x5 over 5 factorial. And this is equal to, okay, I'm going to do x over 1 factorial minus x3 x cubed over 3 factorial plus x5. I should have did plus dot dot dot. Yeah. over 5 factorial, and so on and so forth. Dot, dot, dot. All right. So we have this, and the entire thing can be expressed as a series representation. N equals 0, infinity. Okay, let's see. So x, it seems like we skip one. So I'm going to do, it's x to the 2n plus 1 with -1 to the power of n, because notice that the values alternate between positive and negative. It's like this is a positive value, this is a negative value, this is a positive value, this is a negative value, so on and so forth. So -1 to the power of n over n 2n plus 1 factorial. And you can verify for yourself that this is the correct series representation. And you'll get the first 3 values will be exactly these 3. All right, so we've done this. Let's do 2 more examples. One of them will involve the Maclaurin series, and one of them will involve the Taylor series. Let's just do one for the sake of doing a Taylor series, because I don't want you to get disillusioned that I don't want you to get disillusioned that like it can only work for x equals like 0. It could work for x equals a according to this Taylor series, right? So we're going to do 2 more examples. Eraser. Let's erase the whole thing. Now we're going to talk about Maclaurin series. The first one is Maclaurin series. The last one will be a Taylor series. So Maclaurin or f of x is equal to cos squared x. Now I have to now it's worth noting something. I'm going to use a similar trick I did for the when g of my earlier example, when I did g of x is equal to x cubed e to the power of x squared. Let me manipulate this a bit, and you'll see what I'm doing in a sec. It's nice to know a series representation in advance, because doing cos squared x directly, it's doable, but it's a little messy. So watch. Cos squared x, we're going to use the double angle identity. Cos squared x is equal to 1 plus cos of 2x over 2. And as you know, cos of x could be expressed as this. Cos of x expressed as, I wrote it here in my notes, is expressed as n equals 0 to infinity. What was it? -1 to the power of n x 2n over 2n factorial. I did this earlier, yeah. Okay, so cos squared x can be written, we're gonna, it's better we don't directly try to plug in the Maclaurin formula, because we know what a similar thing here looks like. So 1 plus n is equal to 0 to infinity. Okay, -1 n x2n. Let's see. So this is 2x to the power of 2n. Over, I think, yeah, is this right? Yeah, this is right. Yeah. 2n factorial all over 2. And I'll be honest with you guys, this looks a little messy. I'm going to go expand this out a bit. 1 plus, right? So when n is equal to 0, you basically have, this is 1, 2x. Yeah, so it's 2x. I'm just expanding out this series right here. 2x to the power of 0. Okay, let's see. 2x to the power 0. Let's see, 2. I'm going to do this a long way first. 0 factorial minus so -1. Okay, so 1 times 2x. Let's see. 2 times x. Sorry. Two x squared. Yeah, I'm gonna do this instead. I don't know. Over 2 factorial plus 2x 4 to the power of 4 over 4 factorial divided by 2, it seems like. And this, I'm gonna do this subtract ... 2, it seems like. And then this f of x, expanding off from here, this seems to equal, let's see, so that's 1 plus 1. Yeah, that's 2 minus, okay, so 2, yeah, so minus 2x squared over 2 plus 2x 4 over 4 factorial over 2, and then minus ... All right, and this can be further simplified as, we can rid the denominator completely as 1 minus, let's see, so that's x squared four x squared over 2. So that's 2x squared is 4x squared. 2x squared over 2 plus, let's see, okay, so This is 16x to the power of 4. That's 16 over 4. That's 8x to the power of 4 over 4 factorial minus, okay, so on and so forth. Now, this is equal to, so can I have directly? This is directly equal to 1. You'll see for yourself later that 1 can't really fit anywhere. So what I'm going to do instead is something like this. So 1 plus n is equal to 0 to infinity. Negative 1 to the power of n plus 1. Why to the power of n plus 1? Because the first term here, remember, we're considering these terms. 1 does not fit into this series representation. So it starts off negative. So negative 1 to the power of 1, it gives you a negative value. X to the power of 2n. Yeah. Let me think. X to the power of 2n. Maybe there's 2 ways I could go about this. You know what? I'm gonna say it directly at n equals 1. You could do it at n equals 0, but I'm gonna do it at n equals 1. It makes things a little simpler in this case. So n equals 1, x to the power of 2n. Yeah, now that's negative. That is negative here too. So 2n factorial. Yeah. Let's see, does this work for 8x4? So when n is equal to 2, this is negative 1 squared is 1. Let me think. 2x to the power of, wait, hang on. I feel like something's not right here. I'm missing something. Give me a second. Hey guys, I'm back. This was a very delicate process. I realized I missed a term, but it's all together now. Multiplied by 2 to the power of 2n minus 1. And just to clarify, this is the series for cos squared x. And you can verify this for yourself right here. It's equal to 1 because the 1's right there. Minus, okay, so let's see. Minus the negative, yeah, minus x squared, 2x squared over 2 factorial. What happens when n is equal to 2? You get, okay, so that's negative 1 squared is 1. X to the power of 4. 2 to the power of 2n minus 1. That's 2 to the power of 3, which is 8. And then 2n, 2 times 2 factorial, 4 factorial. Yeah, and minus, and then so on and so forth. That's the answer. Yeah. So we have one more question left to go. How about Taylor for ln x at x equals 2? First thing I'm going to do, there's not something I can directly compare ln x to, so we're going to apply the Maclaurin series directly. So this time it's a Taylor series, sorry, not a Maclaurin series. So Fn of A over n factorial x minus a factorial. This is the formula we're going to be using this time. Now, let's just find a few of the derivatives. So f of x is ln x. F prime of x is 1 over x. F double prime is negative 1 over x squared. I'm going to do about 4 to 6. Use your judgment about how many derivatives you want to use. As long as you can have a representation, a series representation that you feel will, like there's enough derivatives to give you a pattern that you can establish it. F triple prime of x is 2 over x cubed. In case you're wondering how I'm doing this so fast, I already did this ahead of time. F4 of x is equal to negative 6 over x4 f5 of x is equal to, let's see, 24 over x5. And so on and so forth. All right, so let's get to it. You know what? Let's figure out the values for these as well. So I know you guys are thinking I'm making too many steps, but I don't want to make any calculation errors in between. So ln 2 f prime of 2 is 1 over 2 f double prime of 2 is equal to negative 1 over 4 f triple prime is, I know you can simplify it to 1 over 4, but I'm going to say it's 2 over 8. You'll see later why I wrote it in this particular fashion. It gave me a better pattern when I did it this way. F to the fourth derivative of 2 is negative 6 over 16. And the fifth derivative at x equals 2 gives you 24 over 32. When I first did this, I made the mistake of directly simplifying these values. I let values of these fractions. Like I said, this is 1 over 4. This is negative 3 over 8. This is 24 over 32. My advice to you when doing these questions is don't be afraid to make mistakes. Like, you want to approach math, especially calculus 2, like a child going to a candy shop factory. Like, just explore all the options you can. Sometimes I'm not going to make rules of thumb. Sometimes it's good to simplify the fraction. Sometimes it's not. Use your best judgment. How do you use your judgment? You get experienced after doing about 50 or 60 of these problems. There's a saying I learned from my friend Brandon. He told me a person is successful at calculus once he does 1,000 questions on a certain topic. Okay, so here we go. We have this prepared. And now we're just going to expand this formula with the Taylor. So f of x is equal to f, a is 2 in this case, so x equals 2, fn of 2 over n. Oh, I made a mistake here in this formula. It's supposed to be to the power of n. I'm deeply sorry about that, guys. X minus 2 to the power of n. Let's start dumping values in. So when n is equal to 0, f of 2 is ln 2. N 0 factorial is 1, and x minus 2 to the power of 0 is 1, so that's ln 2. At f prime of 2 here, so we get f prime of 2 is 1 over 2 when n equals 1. X minus 2 to the power of 1 over 1 factorial minus, let's see, so minus 1 over 4 x minus 2 squared over 2 factorial plus two over 8 x minus 2. That 8 is so ugly. I'm gonna fix that for you guys. X minus 2 cubed over 3 factorial minus 6 over 16 x minus 2 4 to the 4 over 4 factorial. Let's do one more, plus 24 over 32 x minus 5, no, x minus 2 to the 5th power, running out of space here, over 5 factorial minus dot dot dot. Okay, so we can make this into a series representation. First of all, ln 2 is the odd one out in this case. There's no particular pattern that the rest of these terms fit with ln 2. So we'll just write ln 2, and this will be the so-called quote unquote remainder of the series representation. It just can't fit inside the series representation. And I'm gonna here, since we started at 1 factorial, I'm gonna say that n equals 1. You can use n equals 0 for all you like, but I'm gonna say n equals 1. Okay, so let's see. I found a pattern here. 1 over 2, 1 over 4. I'm gonna just focus on these fractions first, where my cursor is pointing. 1 over 2 then it's -1/4. Okay, so it's very obvious we're going to need a -1 to the power of n, first of all. And then, let's see, so 1/2, what do these have in common? They have in common a factorial. Actually, you know what, I'm gonna, this is n equals 0. I overlooked something. I overlooked something. N equals 0, so -1 to the power of n. Okay, so then this is a positive value. And then these are factorial, so something over n factorial. Over n factorial. And then, or maybe, let's see, n-1. Oh, I know how to do this. I know how to do this. Eraser. Okay, so it's n-1 factorial because 1, so then 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, over 2 to the power of n plus 1. Okay, this works now. Yeah. X minus 2 n plus 1 divided by, let's see, so n plus 2 to the n plus 1, n plus 1 factorial. Okay, and this can actually be simplified. Let's see, n plus 1. This can actually be simplified. N minus 1 factorial. All right. Let me think. N minus 1. 1, 0. Oh, shoot. Oh, shoot. Okay. I'm considering, do I want to make it back to n equals 1 again? Let's see. So n is 0. How about n factorial? N factorial. Seems like n factorial is the better answer. Yeah, sorry. Okay, yeah. N factorial, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2. All right, it seems like that works. And this is equal to ln 2. This can be simplified, like I said earlier, plus n equals 0 to infinity, -1 to the power of n, n factorial over n plus 1 factorial is just n plus 1. Then we'll move this down to the 1. So 2 n plus 1, n plus 1, x minus 2, n plus 1 to the power of n plus 1. And now we are done. And just like cosquared x, we have an oddball out here. So that was, well, that was exhausting. Hope you guys got a lot out of that lesson. Let me know, shoot me an email or like, let me know in the comments section if you want to see any more of this. Thanks very much for watching, guys. I'm trying my best to be like Khan Academy, but it's not always easy. Love to stay, but for now, I got to jump. I'll see you guys on the other side of the bridge. Catch you next time.